Okay, am I audible?
Yes, sir.
Okay. Okay. So till yesterday we studied about testing sequential logic, test pattern generations, BIST, built-in self-tests, and at the end we discussed about some figures explaining how testing of internal circuitry is done using JTAG as well as is done. So our discussion ahead today are discussing these things about boundary scan, which we have abbreviated as BS. So scan testing, boundary scan test and BS architecture or BS cell also. Okay. So these are all concepts. It is theory. So I always take help of some diagrams. I insert them and then I try to explain them. So more explanation is there of the diagram rather than just writing things. So I have copied. Can please mute yourself. You should be careful when you're attending a session. You should mute yourself. My time gets wasted, and also there is a recording. I have to mute everybody. Okay. So this is boundary scan architecture, basically how it is done. So what is in front of us? So we are seeing four square blocks. So these are actually four ICs which are present on a printed circuit board. So gone are the days when a printed circuit board had only one integrated circuit, because integrated circuit was new at that time. But nowadays if we see on a single printed circuit board, not only there are multiple ICs, but also the printed circuit board is also multi-layered. Okay, so many layers are present nowadays. So as the systems have become more and more complex, to achieve that complexity, multiple ICs are required. And these different ICs, some of them are analog ICs, some of them are digital, some of them are mixed signal ICs, and their functionalities are different. uh, there are different ICs who are having different frame formats, different frequencies. They belong to different logic families, and they also follow different communication protocols. So things have become very, very complex nowadays. So as and when the integrated circuits have become complex, the testing of these ICs has become even more complex. So in order to save time, usually what happens is that all the ICs which have to be tested for faults, they are all of them are put on a single printed circuit board, and this boundary scan architecture or boundary scan technique is used for testing all of them by connecting them. Okay. So because the boundary scan technique provides a standardized serial scan path of an IC, that is why it is possible to test multiple ICs by connecting them in series or parallel. Okay, so we write a few important points here. So we say that BS stands for boundary scan. So boundary scan provides a standardized serial scan path through the IO pins of an IC. So you will appreciate this statement when we see some more diagrams related to boundary scan technique. Okay, and as I told you that BS is IEEE standard 1149. Okay, so boundary scan is IEEE STD 1149. Okay, now the above figure shows multiple ICs put on a single printed circuit board, and this circuit board is called as a test bed. Because the ICs to be tested are all put on the same printed circuit board, and they are all being tested using boundary scan technique. This printed circuit board now is called as a test bed. So above figure shows multiple ICs put on a single printed circuit board, and ICs can be connected in series or parallel. ICs to be tested can be connected in a variety of series and connections, enabling the testing of a complete system. And the different tests which can be carried out using boundary scan technique, the different tests done using BS technique are sampling, inputs and outputs, that is called as reading, or it is also called as observability. Observability. So observability means actually it is reading operation. When we say sample, we will sample an input or an output to read it, so it is observability. And when we say setting the inputs and outputs, it is called as controllability. Okay, it is called as controllability. So it is called writing operation. Then connectivity between components. And fourth is distribution and collection of BIST results. So BIST stands for built-in self-test. Okay, this. So now we have another figure which helps us to understand things better. So in the first instance, it is difficult to understand. So we can actually write something now. Okay. So this is the first time you are seeing a system something like this. Okay. If you carefully see, these are identical components. You see here. Just a minute. You see here. 2 and 3. If you carefully see, it has something which we have seen before. It also has something which you have not seen before. So before we have seen a component which has an input D, a clock input and output Q. So in the first site we see that it is actually a D flip flop, but there is a different kind of a D flip flop. It is called as a dual port D flip flop. So it is an advanced version of a flip flop. Usually a D flip flop has one D input, one clock input and one output. So here we have two inputs D1 and D2. We have two inputs D1 and D2. Also we have two clock inputs C1 and C2, and it is having one output Q. Okay, so all the three flip flops are having a single output, but each flip flop is having two inputs, so it is called as a dual port D flip flop. Similarly, each flip flop has two clock inputs, and it is very simple, 1 for 1 and 2 for 2. So whenever the flip flop is pulsed at C1, whenever it is pulsed at C1, whatever is present at D1 is sent here. Okay, so whenever the flip flop is pulsed at C1, that is, if I apply a pulse here at C1, what happens is whatever is at the input D1 will be sent to the output here. On the other hand, if the flip flop is pulsed at C2, then whatever is present at D2 will be sent to the output. Got the point? And there is one output Q. This is a combination logic here. So combination logic, it accepts n number of inputs X and it generates m number of outputs Z. Now this combination logic is also responsible not only to convert the inputs X to the output Z, it is also responsible for generating the next state inputs for the flip flops. So while Q1, so we see here, so Q1, Q2 up to Qk are called as the present state outputs. Similarly, Q1 dash, Q2 dash and Qk dash are the next state input. That is, if I want to take the output Q1 from 0 to 1, then the value of Q1 dash should be 1, so that whenever the D flip flop receives a rising edge at the input C1, at that time that 1 will be inserted into the flip flop, it will be stored, and hence the present state Q1 equal to 0 will be converted into Q1 equal to 1. Okay, we also see that there are two clocks here. Okay, so this is SCK and this is TCK. So SCK is the system clock or the normal clock, and TCK is a test clock. That means this particular setup has the ability to operate as a normal D flip-flop based system. It is called as a normal mode, and at the same time, if you want to test it, then you can also test it. So SCK is a system clock which is applied to the first clock inputs C1 of each dual port D flip-flop, while TCK, that is the test clock, is applied to the second input C2 of the individual flip-flops. So when I want to operate this system in the normal mode, so what I will do, I will not apply the clock TCK. So the D flip-flop will not be pulsed at C2, but it will be pulsed only at C1. So we know that if the D flip-flop is pulsed at C1, the D1, the input at D1 will be stored inside. On the other hand, if I pulse the flip-flops at input C2 using TCK, that is test clock, at that time the D2 is activated, and hence SDI, that is serial data input, will come into picture. Okay, so in essence we see here the combination logic. Now what we will do, whatever we have explained, now we will write it in words, so whenever you want to refer, you can refer it. Okay, so we'll reduce it so we can see it. Okay, first is that there are k number of dual port D flip-flops in the system. Okay, so Q1, Q2, Q3 up to QK, they are outputs of K dual port flip-flops. Second important thing is that each flip-flop has two inputs, D1, D2. Similarly, each flip-flop so each flip-flop has two clock inputs, C1, C2. Each flip-flop has one output. Now, when flip-flop is pulsed at C1, input at D1 is stored. When flip-flop is pulsed at C2, the input at D2 is stored. Okay. SCK is the system clock for normal mode. TCK is the test clock for test mode. Okay. Combinational logic. So what are x1 to xn? Very simple. x1, x2, x3 up to xn. They are called as input test vectors for testing. They are input test vectors. Z1, Z2, Z3 up to Zn are the outputs. Z1, Z2, Z3 up to Zn are the standard output set. Also Q1, Q2, Q3 up to Qk are the present state outputs, while Q1 bar, Q2 bar, Q3 bar up to Qk bar are the next state input set. Okay, so present state output set and next state input set. So what is a function of combination logic? Combination logic has the following functions. So combination logic it converts the inputs X into Z, and it also converts X into Z, and also generates the next state inputs. Sir, it also generates QK dash, because I can say so it uses a combination of X comma Q to generate QK dash. Okay, this is it. Okay, this was the description. And SDI is scan data input and SDO is scan data output. SDI comma SDO, they are scan data input and scan data output.
Hello.
एक मिनट hold. The test procedure can be said something like this. The test procedure is summarized as follows. Scan in the test vectors. Xi using TCK, comma SDI. Second is observe the standard output set Z. Third, apply one clock pulse of system clock to store the new values, that is Q1 dash to Qk dash in the system. Scan out and verify. Values by applying one pulse of TCK. Repeat steps 1 to 4 for each test vector. Okay, fine. Okay, so we covered with scan testing, the boundary scan test now. Fine. So the diagram which we are seeing here, we can give the title to this figure as IC boundary scan register and test access port, TAP. Okay. TAP. So TAP is a very famous thing. It's called as a TAP or test access port controller. Right. So this is our test access port. And these are the 5 signals which we also mentioned yesterday: test data input, test data output, test clock, test mode select, and test reset. Okay. And these are the IC pins. So we'll highlight them also. These are IC pins. So we can say these are called as BS cells or boundary scan cells. Okay, so we can clearly see. So what is there in between? So here we are having our core logic of the IC. Okay. Core logic. Okay. So in between the IC pins and the core logic, we have boundary scan cells. Okay. So between the IC pins and the core logic, we have boundary scan cells. Same here also. Between the IC pins and core logic, we have boundary scan cells. And then we are having what is called as a test logic and tap controller. Okay. So the only difference between an integrated circuit which is not having boundary scan ability is that in that IC there is a direct connection between the IO pins and the core logic, while in an IC which is boundary scan ready or boundary scan compatible, we have boundary scan cells between the IC pins and core logic. Okay, so we can therefore make a statement that in a conventional IC without DFT, this is the right word, in a conventional integrated circuit without design for testability support, the IO pins are directly connected to the core logic. While in an IC with DFT, there are BS cells between IC pins and core logic. Okay, and these are standard JTAG signals. So now we have typical boundary scan cell. So we have the 0 input of multiplexer, 1 input of multiplexer, 0 input and 1 input of multiplexer. Okay, here we have the TDO, that is test data output. We have TDI serial in. So now there is shift and load here, and there is test or normal here. Naturally, if this signal is connected to 0, and this is connected to 0. Okay, so if we have 0 here and 0 here, then this input is selected. So when I say this input, that means what? Whatever is the data coming from core logic or from the input pin will be sent inside the IC. Okay, clear? So when this is 0, it is called as load. Load what? What to load? The input data or data coming from core logic is to be loaded. Is it clear? Yeah, so we can actually write a very simple to understand. Okay, so we have TDI or serial in. Okay, so data is coming from here. Basically shift register. Shift right. Okay, so we can write down like this, that first, if shift or load equal to 0 and test slash normal equal to 0, then data from input pin is stored in the D flip-flops and also shifted right on arrival of rising edge of the clock. Okay, so these are all edge triggered systems. This is positive edge triggered. This is also positive edge triggered. Okay, both of them. Okay, so on the other hand, if shift or load equal to 1, and also test slash normal equal to 1, what will happen is this thing. This is 1, this is 1. Then this will be selected and this will be selected. Okay, so whatever data is coming from here, it will go here, it will go here like this, and then this will come here. It's okay, like that. Then the data from TDI pin from test data input source will be stored in D flip-flops and also shifted right on arrival or rising edge. Okay, it's very simple to understand. And then finally we have the boundary scan architecture. One thing I forgot is that yeah. So we stop here. The remaining part of this includes the last part of the unit, that is tap controller, which is a very important topic which is asked almost every year, maybe since the last 10 years. Okay.